Okay, so hello everyone, I'm Florentin. I'd just like to take this quick opportunity to thank the organizers. They've done a fantastic job with this conference. So I'm doing my PhD in Oxford with my supervisors, Coralia and Armin, and I'm going to present work that's done in my PhD on nonlinear matrix recovery, also known as high-rank matrix recovery. So this is going to be an extension of low-rank matrix recovery or low-rank matrix completion. So what do we mean by that? So low-rank matrix completion is a well-investigated field of research where we're given a matrix, and let's say it's n by s, and it's full of holes. There are missing entries, and we want to fill in these missing entries. Now, in general, there are infinitely many possibilities to fill in the entries, but we make the extra assumption that there's a low-rank matrix that can fill in those entries. And the fact that this matrix is low-rank introduced some redundancy in the matrix. There's just too much information because it's low-rank. And so the low-rank assumption allows to complete the matrix in a unique and well-defined way. And so what people solve in this field of low-rank matrix recovery is they want to usually minimize the rank of a matrix, provided that it satisfies some linear measurements. And so these linear measurements that I write generally AX equals B, it could be the entries in the matrix that I know, but it could be a different type of measurement, such as a simple linear system of equations that X satisfies. So that's for low-rank matrix completion. We want to minimize the rank of a matrix under some linear constraints. And people have looked at various formulations, optimization formulations to solve this problem. And some are convex, some are non-convex. And so I'm going to present one that I'll use in this talk for the extension that we're considering. So to try to recover a matrix from missing entries, essentially, we need to replace minimization of the rank because that's a non-smooth cost function and it's very difficult to optimize. So what we do is we use the Grassmann manifold. So the Grassmann manifold is the set of all the linear subspace of a given dimension. So I'm going to have a variable u that's a subspace. I'm looking for a subspace, and I fix the dimension. And the dimension of that subspace is the known rank of the matrix I'm trying to recover. So here there's a key assumption. I'm assuming that the rank of the matrix is known. I still have my variable x that has to satisfy the entries that I'm given. And this is the cost that I'm trying to minimize. What's this cost? It's minimizing the difference between x and its projection on the subspace. So if this cost is 0, x will be fully contained in an r-dimensional subspace, and so we'll have rank r. Right? So if I can get the cost to 0, x will be rank r because it will be on an r-dimensional subspace. And so it's a roundabout way of minimizing the rank of x, and this happens to be a smooth function. So it's much nicer to optimize than using the rank. And in this talk, we'll use this formulation again in a slightly more general setting. So in this talk, we want to do nonlinear matrix recovery or high-rank matrix recovery. And so what that is we replace the assumption that the matrix is low-rank with an assumption of nonlinear structure. So if I look at the columns of my matrix, I'm going to assume that these points not necessarily live on a unique low-dimensional subspace. It was the case here, but they could be on something else. And it could be, for instance, these columns define a bunch of cluster as a point cloud. Or perhaps they could be on on a union of subspaces. So they might not all be on the same subspace, but they will be on a union of several subspaces. And that's a model, this union of subspaces that's been used in data science quite a lot. And more generally, we could consider a structure for this point cloud that is nonlinear and smooth, and we'll see how we're able to handle that. So this is going to be the assumption that we have some information on the structure of the points in this matrix, the columns, and it doesn't have to be low rank, but it's going to be something else that we'll be able to exploit. And how do we exploit this? Well, this is really the the main conceptual idea in the talk, I would say, is that we're going to have a lifting, so a map that takes every column in X. So X is the matrix that I would like to recover. But so conceptually, I take every column in X, and I'm going to map them to a higher dimensional space. Right? I go from R small n to R big N. So I'm taking them to a higher dimensional space. And phi is going to be a nonlinear map. And the hope is that if I stack in a matrix that I call phi of X, the lifting of all the columns of X, I guess all these phi of Xi, this matrix will be low rank in this higher dimensional space Rn. So really the idea is that have a nonlinear structure here, X is full rank, but I can find a phi that will expose the nonlinear structure, and in a different space, then it will be low rank. So the trick will be to find some structure in the original space and some map such that the structure becomes low rank in the lifted space. And if the points in the original space are just in a sort of arranged in completely random manner, then they don't satisfy some structures such as clusters or several subspaces, then it will still be high rank in the original space. Okay, so, and very soon in the talk, I'll give precise examples of types of structures we can exploit and the associated lifting, the associated map. All right, so this is exactly what I said. We'll assume that there's a map such that phi of X is low rank, the lifted matrix. And now if you've understood that, then you could take back what I described as an optimization problem to recover low rank matrices. I gave that a few slides ago. And you could turn it into an optimization problem that will recover high rank matrices if I give you this map phi. Because now what we want to do is we still have these two variables X and U. X still satisfies Ax equals B, so the entries that I know in the matrix, and I want to find the other ones. And I still have this subspace variable, still looking for subspace, but now I'm not trying to make X fit to a subspace. I'm trying to make phi of X fit to a subspace. So this is approximating the minimization of the rank of phi, the rank of the lifted matrix. Okay, so in this talk, we'll focus on trying to solve this. And I give examples of phi and examples of optimization methods we can use, especially given that this constraint is a nonlinear constraint, happens to be a Riemannian manifold, which we can exploit, but it's a bit tricky. So now let's go through examples of structure for which we have an appropriate lifting. So this is something that was introduced in the paper by Greg Ongi in 2017, and it's the algebraic variety structure. And so they introduced a way to complete matrices that have this structure. And so for this algebraic variety structure, one should use the monomial map. So how does this work? So I have my original matrix, and I'll take one column, the first one, and then I'm going to lift the first column and put it in the first column of phi of X. And what's the monomial lift doing? It's creating all the monomials up to a certain degree given these variables. So here I have two variables. So my point cloud is S points in R2. And I create the monomials using these two variables. So I have the first order terms, then I have the second order terms, there's the cross term, and then the power 2. So, and here I'm just giving an example with d equals 2, but I could go on further, and that would give like a different model for my recovery. But let's say here that's the monomial map illustrated for degree 2, and I apply this map to every column. Take every column, and I apply this map, and I get this lifted matrix. And the trick is that if the column of X satisfy polynomial equations, so algebraic variety, I don't remember if I said that, but it's a surface or set that is defined by one or several polynomial equations. So if all my columns of X, if these points in R2, if they satisfy the same polynomial equations, they are on some algebraic variety of some sorts, and that will make phi of X rank deficient. The reason why phi of X is rank deficient when X is an algebraic variety I I'm just hiding a little bit of maths, but it's not very complicated. It's something that's well explained in this paper by Greg Onji. So if my point cloud is an algebraic variety, then I have this monomial feature that will make the lifted matrix low rank. And subnote that a union of subspaces, which I mentioned earlier as an interesting model that comes up in practice, it is a case of algebraic variety. So this is just to note that the monomial map would apply to data that belongs to a union of several subspaces. And this is just a numerical illustration of what I've explained. So I've generated 3 subspaces of dimension 1 in R3. So I've spread a bunch of points, 20 on each subspace in R3. So I have a very fat matrix 3 over 60, and it's full rank. It's rank 3 because the subspaces are not aligned. And so in the original space, X is full rank. But if I take phi of X with my monomials up to degree 5, then I have a matrix that's 56 by 60, and that matrix happens to be rank 16. And here I'm showing the singular values in log scale. But the point is that because X is a union of several subspaces, even though X is full rank, phi of X is low rank. And that's really the sort of the beauty of this approach, is that we have a way to exploit a nonlinear structure and somehow bring it back to a framework where we're minimizing a rank of something. Okay, now let's move on to the second and last example of some type of structure that we can exploit in the point cloud. And this is going to be when the points are grouped as clusters. And so let's define the Gaussian kernel. So Kij, so for 2 points ij, so two of these points ij, Kij, which is this Gaussian kernel, it's going to behave like 1 over the distance, essentially, right? Because if you think about the exponential, if xi is close to xj, then the kernel Kij is going to be close to 1. And if they're far from each other in norm, then the kernel entry is going to be close to 0. So we're forming this kernel matrix, which you should think of exactly as the map phi that we talked about. There's a bit of technical details, but it's really K, the kernel is exactly like phi. And so you're going to build this lifted matrix, and it's going to have sort of the matrix is a square matrix with indices of all the points. And so the entry Kij of the kernel corresponds to the interaction between the point I, the point xi, and the point xj. And so if my points are grouped as clusters like this, then I would have a kernel matrix that looks roughly like this. So all the points in the first clusters, they would be close to one another, so the kernel entries would be close to 1. And the points in the second cluster, again, they would be close to one another, so the interaction would be close to 1. And for the off-diagonal blocks, the points are in different clusters, so they're far apart, and so the kernel entry would be close to 0. And this matrix has rank 2. And in general, if I had more clusters, I would have the same matrix with roughly 1 on the diagonal and 0 off the diagonal. So the rank of this matrix is roughly the number of clusters. Now, it's not exactly that number of clusters, because these entries are not exactly 1 and not exactly 0. So there's a bit of, it's like a numerical rank. There's a bit of noise, but roughly the rank is close to the number of clusters. So if I have 300 points and I have 3 clusters, this matrix is going to be 300 by 300, and it's going to have rank 3. So it's clearly going to be rank deficient in the lifted space. Although 3 clusters in our something are usually not going to be rank deficient. Okay, now let's talk about algorithms that we'll use to solve the optimization problem that I formulated earlier. So, and then we'll present two optimization approaches. The first one is alternating minimization. So I just recap the optimization problem here. We have 2 variables, u and x. And so one option is to just say, I'm going to fix one and fix x and solve over u, or I'm going to fix u and solve over x. And I'm going to repeat like that. I'm going to alternate. And it turns out that optimizing over u is something that we can solve to global optimality using a truncated SVD, because this amounts to finding the subspace that best captures the energy of the matrix phi at xk. So here I'm talking about xk, uk, because I'm thinking about an iterative algorithm that starts at x0, u0, and that will update x and u iteratively to converge to hopefully the solution of the problem. So u is easy to solve because we just do an SVD of this matrix phi, and then we will truncate it to dimension r, and then we'll keep these singular vectors. So that's how we can update u. When we fix u and we update x, this is a non-convex cost function because phi is usually non-convex. If you take polynomials up to degree 2 or more, it's going to be non-convex. And we still have these linear constraints on the matrix X. I didn't note that we're considering a noiseless case with respect to the measurements. So potentially you could not trust your measurements so much, and then you would have to do something else. But here we'll just assume that we know exactly that the matrix satisfies some measurements exactly, so we can treat it as an explicit constraint. So that would be alternating over u and x. And it's sort of depicted like this. As I said, you start with an initial guess, you do a singular value decomposition to update u, and then you would do any method that you like, really, to update with respect to the variable x. And so, for instance, you would do some gradient steps, and then you would move on like this and iterate. And we have a couple results regarding this alternative method. So under reasonable smoothness assumptions of the problem that are going to be met in practice, in the limit of this iteration process, the gradients of the problem will converge to 0. So in the limit, we'll converge towards a stationary point. And we also have, in addition to that, a complexity result that will say it's a global complexity. So that means wherever I start, how poor doesn't matter if my initial guess is really poor, I will converge to the stationary point. And if I want my gradients to be smaller than some epsilon, then the number of steps that I will have to take cannot be more than something. And this is the something. And it depends on problem constants, like how far do you start from the solution. And also, it depends on 1 over epsilon squared. So if you're greedy and you want a very small epsilon, then your bound is going to be large. Okay, in the worst case, you'll do many steps, but at least you know that in the worst case, you'll get there in some finite number of steps. And now let's talk about a second framework to solve this optimization problem, which is known as optimization on manifolds. And in this framework, because here we have this Grassmannian, which is a nonlinear manifold. So as I said, it's the set of all the subspaces of a given dimension. So it's sort of not easy to represent in one's mind what this space really looks like, but it turns out to be a smooth manifold, and people have developed tools to optimize over such sets. And just as a brief introduction, what people do when they're optimizing over manifolds, here I'm just showing the sphere. They construct the tangent space, and it's unique because the manifold is smooth. And then they want to go in some tangent direction to decrease their cost function, and then they'll have to project back onto the manifold to stay feasible. So these Riemann optimization methods, they're optimizing cost functions over manifold, and they're staying feasible. So this is a constraint. They have to start on the constraint, and then they'll travel along the manifold while using the tangent space and expressing the gradient as a vector in the tangent space, and the Hessian as an operator that acts on vectors on the tangent space. But so anyway, so here we have this manifold we have 2 variables. So it's a Cartesian product of the Grassmannian variable, this U subspace, and also the matrix X, which is here just a linear manifold. So it's not really a problem. Oh, I went back. So what do we do when we're optimizing on Riemannian with the Riemannian manifold approach? Well, we use what's known as the Riemannian thrust region algorithm. And so what's a thrust region? Well, it's sort of a sister method to the Newton method. So it will just be, instead of doing a line search, as you would do for more classical optimization methods, we're not going to do a line search. We're going to use a thrust region. So we're going to build a model of our function. Here, this model is second order because it uses the gradient and the Hessian, but potentially it could just be a first order model. And instead of a line search, we're going to have a safeguard that says, I only trust my model within a certain radius, a certain ball around the current point where we are. So if I'm at some iterate UKXK, I build a model that uses the derivatives at UKXK, and I only trust the model in some ball of radius rho here. And then we're going to optimize this model inside the ball. And if we find that the decrease that we get matches with the function decrease. So if we find that, essentially, the idea is just that if we find that the model is a good match for the function, that's great. Then I'm just going to accept the new iterate that I found when I was solving my model over my ball, and I'm going to move on. However, if we solve the problem of this minimizing this model over the ball constraint, and we find that the decrease in the model doesn't match the decrease in the function. So we realize that the model is not a good representation of the function. That means that the thrust region radius is too large. So we reduce the radius of the ball and we continue again. Okay, so that's just how the thrust region method works. But it's just what we used as a Riemannian optimization method. And the good thing is that it's a second order method because it uses the Hessian. So we'll see in the numerical results that it has some advantages. And so we're partly using this MANOP toolbox. It's a MATLAB toolbox, and this is great if you're interested in optimization on manifolds. This is probably where you should investigate, and that's what we used, and it works quite well. So, and now I showed guarantees in terms of convergence for the alternating minimization method, and they have equivalent in Riemannian optimization. So for this Riemannian thrust region method that I presented, I can also give a bound on the worst case number of iterations and to reach an approximate stationary point. And this will be the same order of magnitude with respect to epsilon. Now, this is the thrust region. If I use a second order model, it's a second order method, so I can guarantee that I will find second order stationary points. So points where the Hessian is almost positive semi-definite. And that takes more work. So now the complexity is in 1 over epsilon to the 3, whereas if I just wanted a first order, like earlier, it was 1 over epsilon to the squared. Sort of a detail, but both of these methods have some complexity guarantees. Okay, now to finish, let's look at some numerical results that we got while recovering these high-rank matrices that have some nonlinear structure. So this is a comparison of 2 optimization methods. So the 2 optimization methods that I described, the blue one is the alternating. So I'm alternating between singular value decompositions and gradient steps, so first order steps. And the orange is the Riemannian thrust region. So when I'm on the manifold and I'm building a second order model with the Hessian. And so this is the y-axis is the gradient norm in log scale. So, and this first plot is with respect to time in seconds, and the second plot is with respect to iterations. So if we look at the right-hand side plot for a second, we'll see that early on, it's the blue curve that makes the more progress. But then if we're interested in, so this will be nice if we're not too greedy in terms of accuracy. So if I'm trying to recover my matrix, I have a point cloud, and I know it's a bunch of clusters, and I want to recover them. If I'm content with accuracy, maybe 2 or 3 digits, 2 decimal points, then I should probably go for the blue method because it's a first order method and it makes a lot of progress fast. However, if your application requires a lot of accuracy and you want to recover this point cloud for which you have missing entries somehow to a very high accuracy, so maybe you need 10 to the minus 6 accuracy, you need 6 digits, then you would want to use the orange method, so the Riemannian second order method, because near the minimizer, it converges really fast. It has a quadratic convergence rate. And the left-hand side plot is showing the decrease with respect to time. And here we can note that the second order method in orange doesn't do as well because each iteration is more costly, right? So it's a second order method, so each step is going to take more time. But still, if we want a lot of accuracy, then we should still use the second order method. Okay, so that was just comparing how the two methods behave on a normal problem where I was trying to recover a high rank matrix. Going back again. Let me just take a sip. So now we're going to address the following question. All right, I have this matrix. I know it has some structure. Let's say that I know that the columns of my matrix, they belong to several subspaces. And I know that I can use the monomial map to make this low rank in the lifted space. Now, I have this non-convex optimization problem, and I showed you some optimization methods to try to find stationary points. The thing is, there's no guarantee a priori on the quality of these stationary points, right? Because the problem is non-convex, we could find a stationary point that's really far in terms of function value to the global minimum, right? We could get stuck in a bad local minimum. So these numerics will try to answer the question, when do we actually recover the original matrix when we solve these optimization problems? And so these are problems where we have a number of subspaces and we initialize randomly, so that the initial guess is random. And so here we've solved a large number of problems and we varied, I hope you can see, but this is the y-axis is the undersampling ratio. So that is the percentage of entries that I know. So really down below, it's problems where I only knew 10% of the entries. And up above, there are problems where I knew 90% of the entries. And then you have all the range, right? So in the middle, you knew half the entries in your matrix. And here we have several subspaces, and I'm increasing the dimension of the subspaces. So I could have a few subspaces dimension 1 here, then have the same number of subspaces of dimension 2, dimension 3, and so on. And for each scenario, so when I knew 70% of my entries and I had subspace dimension 2, for each scenario like this, I solved the problem 50 times, like a random problem, randomly generated problem 50 different times for random initialization. And the instances so the grayscale here is that what's in white is when we recover the original matrix. So the optimization solver reaches a point that is the solution, that is the matrix that I want. And in black, it's instances where we don't recover the original matrix. So the matrix completion failed. And so we see that naturally, when we're going down here, we're seeing less entries. So the recovery is harder. And as well, when we're moving up the x-axis, we're increasing the dimension of the subspaces. And so the problem is getting harder and harder because it's really, there's less and less structure because I have subspaces of very high dimension. So it's better to have many subspaces of low dimension rather than a few subspaces of a large dimension. It's a structure that's we're not able to exploit as well. And this plot is when we use the first order method, the alternating method, and this plot is the same recovery plot for the Riemannian second order methods. And so what we see is that they behave very similarly, right? Whether we use a second order or first order method, they recover with roughly the same performance. And what I say when I mean recover is that we need to be at the distance 10 to the minus 3 to the original matrix. Okay, so that's what I would call a low accuracy. And if now we're greedy and we want to recover the matrix with a high accuracy, so say I want to be close to my matrix in distance 10 to the minus 7, then we see that the first order method does much worse, right? There's a lot more black on this plot compared to this plot. However, the second order method, when I change from low to high accuracy, the recovery is less effective, let's say. So what that means really is something that I mentioned before. If you want a lot of accuracy, you better use the second order method, because it won't stall when it gets near the minimizer. And it will converge faster near the minimizer. All right, and so this last example has to do with clustering. So now my original point cloud is a bunch of clusters, and again here this is varying the sampling rate. So how many entries do I see in my point cloud? And this the grayscale, again, there's only one point on the y-axis. The grayscale is saying which cases can I get the correct clustering at the end after I've completed. And so if I can see up to 50-40% of my entries, then I have a chance to recover the correct clustering. If I see only 30% of my entries or less, then my clustering is going to be wrong after I've completed the matrix. Okay, so I guess I'm pretty much on time. I was lucky to get a few extra minutes. So let me conclude. So what I presented today was the concept of nonlinear matrix recovery, or high rank matrix recovery. And that is when we have a matrix with missing entries, and it is high rank. So it is an extension of the low rank case, but it has some nonlinear structure. It's high rank, but it's not random. It has some nonlinear structure. And we're able to use a kernel or some sort of nonlinear lift that will expose the structure, and we'll be able to bring it back to some sort of rank minimization problem. And I presented a couple algorithms, one that was alternating using SVDs, single value decompositions, and one that was a Riemannian optimization algorithm. And both of these methods have worst case complexity bounds to ensure convergence to your stationary points. And numerically, we were able to see that for a wide variety of cases, depending on the number of measurements and so forth, that these problems, when they're solved, recover the original matrix. Right? So it's a nice extension of low-rank matrix completion to some high-rank case with a variety structure. So in the future, one thing we would like to do is maybe speed up these methods and also come up with a theoretical proof that will recover the original matrix, which is not the case at this point. At this point, we're only observing that it works numerically, and that the stationary point that the algorithm finds happens to be the global solution, but there's no proof of that. So that might be, but something we're actually working on already. But hopefully that will come out at some point. So thank you very much for following me, and I guess now we'll open to questions. I'll come back to Zoom.
Thank you, Florentin, for your talk.
Sure.
If there are any questions, please write them in the chat.
Yeah, Margaret.
Yes, Margaret.
So if you go, it was all the way back on slide, I think it was slide 4. So you had your optimization problem.
Yeah.
And you had this R, which is your what you think the rank is in this new high dimensional space. Is it slide?
Yeah, this.
Yeah. So how do you know what this R is? It's something that needs to be fixed for your algorithm. Am I right? I might have understood wrong.
No, you're completely right. So we need to guess what the rank is to feed it to the algorithm, because we're defining U to be a variable of a certain dimension. So we need to know what R is, or at least have a guess. It turns out that if we don't know exactly what R is, the performance decrease. But as long as it's a fairly tight upper bound, it's not too bad.
Okay.
But so to answer your question, when we're talking about clusters, the rank is the number of clusters. So
Okay.
that's maybe we can argue that we could guess that. When it comes to a union of subspace or general polynomial variety, it's more difficult. There are some bounds that I didn't put in the slides that say that if I have maybe k subspaces of dimension d, then the rank is upper bounded by something. But it's like a difficult maths problem to guess the actual rank, and there are only upper bounds that exist, and they're not tight. So in general, it's a fair concern whether we can get a good estimate of the rank.
Yeah.
Good question.
Okay, Mel has also a question, so I will unmute her.
Hi, great talk. I was
Thanks.
gonna ask about two, if that's okay. Have you considered using like a hybrid method of the two? And then as in starting off with your alternating minimization approach and then switching out to LTR to kind of get the best of both regimes?
Yes, great question. So when we're alternating, there's a singular value decomposition step, and then there's a step which we can't do really much about. Well, we could do random SVD, but let's not get into that. When we're minimizing over X, here I just said, okay, let's do gradient steps. Turns out we could also do a second order method that uses the Hessian. We could also do a truss region on these constraints. And so yes, we've tried that. We've tried using for this step. So there's the second step of the alternating. We've tried using a truss region that uses the Hessian, and interestingly enough, if I go back to the end, yeah. So it doesn't change the shape of this plot that much. So even if you're using a second order step when you're alternating, the fact that you're alternating is actually quite bad, and it will prevent you to get quadratic convergence, even if each step is using the Hessian, which is an interesting thing. So actually, alternating is a popular thing because usually each sub-problem is something that it's easier to solve, and maybe we have a formula for that. So that's convenient to implement and analyze, but in fact, it doesn't have good convergence properties.
Is that that's not quite the same as if you say initialized your other method with a point that's a couple of iterations of alternating minimization and then.
Okay, yeah. So I think I understand what you meant now. So what you're saying is I'm going to do the blue method for a while, and then I'm going to pick up. Yeah. So that's a great point. And then if one would need to get the results on a large data set and performance was relevant, then they should probably do that. But we didn't.
Cool, thanks. And if I'm all right to ask another one, your final result on cluster recovery doesn't seem dependent on the number of clusters. Is that just because of how your result has been worked through?
This plot doesn't present that, but we found that if you increase the number of clusters, then the recovery is more difficult because the points are going to be just simply less spread out.
Oh, right. Sorry. So this result only applies with
this plot doesn't show it, but this plot doesn't show it. But if you increase the number of clusters, essentially what drives the recovery is whether or not the clusters are far apart. So.
Oh, okay.
Yeah, but no, this plot doesn't translate that.
Cool. Thank you.
Yeah, you're welcome.
Hope
you're doing well.
Going over time, but if you could just very quickly comment on the stopping criterion in your numerics.
Yeah, thanks. So yeah, and maybe you're wondering about this, especially with respect to the recovery, but let's say that so the stopping criterion is the gradient norm. So we're just saying we want the gradient norm to be lower than 10 to the minus 7. And if you can't get there in a reasonable time, then we'll stop you. If you completely stall at 10 to the minus 4, then we'll cut you off. But so the gradient norm was the tolerance.
what is, I mean, is there some relative convergence? Like, did you, well, I mean, okay, first of all, what is the maximum number of iterations?
Maybe like 1,000.
Okay.
Yeah, from memory.
Thank you. With this,
yeah.
Move to next speaker.
Thank you very much. Thank you for following, everyone. I have another question. Let me think about it. Oh, Cynthia. Okay, thanks, Simon. You asked it. Yeah. Yeah, Cynthia, if you're interested, you can always send me an email. Thank you for your question.